Welcome. The purpose of this lesson is to be able to estimate limits given a graph or by graphing a function on a graphing calculator, and to develop the understanding that the value of the limit and the value of the function are not necessarily the same values. You'll also learn and apply the formal definition of limits. So can we also find limits graphically? Well, the answer to that is yes. Right, so we're going to take a look at the limit of x squared minus 3 as x approaches 2. Right? Notice the parentheses there is telling us we're taking the limit of the whole thing. You should remember if the function that you're taking a limit of has more than one term, you should remember to use parentheses. So let's graph this function. Right? So this is just a standard parabola, but it's been shifted down 3. Right? So instead of 0, 0, it's going to have a point at 0, negative 3. And normally this would be 1, 1 and negative 1, 1, but now it's been shifted down 3, so now they're at negative 2. Right, and then 1, 2, 3 right here. Right, so again, these points here I just drew in would be at 4, but now they're just 4 away from our vertex. Right, and I'm going to graph one more point in there. 8, 9 right there. All right, so it's just a standard parabola that's been shifted down 3. There it is. And so we want to find the limit as x approaches 2. So that means we need to look at the limit from the left-hand side and the right-hand side. Well, we can see from both the left and the right, our limit here is approaching the point 1. Right? So that's even a point on our graph, right? F of 2 happens to be 1. So this is a continuous function. Oops. Yeah, I'll just write it again. So the limit as x approaches 2, x squared minus 3, is equal to 1. That's our limit there. So we can see that from our graph. Here we have some more graphs, and these are in your notes. We're going to look at number 1 and number 2. Number 1 is f of x equals x squared plus 2x minus 2. First of all, we're going to find f of 2. That's just the value of the function when x is 2. And we can see right there, right, 2, 6 is a point on our parabola. So f of 2 is equal to 6. So you can answer these along with me. The limit of f of x, and by the way, I can use f of x because we've established that f of x is our graph here. So the limit of f of x as x approaches 2 from the left, right? So if I come from the left, from the negative side, right, we can see that our limit is still 6. So the function is approaching 6 when x is approaching 2. We want to find the limit of f of x as, oops, and I think this accidentally got erased in yours. It was just making a slight correction, and I think my plus disappeared. So if the plus disappeared from your notes, just put the plus in there. So the limit of f of x as x approaches 2 from the right, well, look at that. As we get closer and closer from the right-hand side to x equals 2, the limit is 6. So our function is approaching 6. Since our left f of x as x approaches 2 is 6. Let's look over here at our other graph. So now this one is f of x equals x squared plus 2x minus 2, but x is not equal to 2. Right, so f of 2, right, that's no longer 6 because there's a hole in our graph. Right? So f of 2 is going to be does not exist. That point does not exist. How about the limit of our function as x approaches 2 from the left? We see if we come from the left, right, the graph is approaching 6. The limit of f of x as x approaches 2 from the right. If we come from the right, right, our function is approaching 6. Right, so our left and our right hand limits match, so the limit of f of x as x approaches 2 is 6. So notice that the existence of a limit at a given point is independent of whether or not the function is defined at the given point. It doesn't matter that there's a hole in our graph at 2, 6. The function is still approaching 6 when x is approaching 2. So that would be the limit as x approaches 2. And we're going to take a look at some more. There we go. All right, so this one's not in your notes. Let's take a look at some more. Evaluating limits graphically. So here we have a rational function. It is undefined at x equals -1 because when x is -1, the denominator goes to 0. However, x equals -1 is not a vertical asymptote. We could factor, right? So that numerator factors to x plus 3 times x plus 1. We could cancel out the two x plus 1. I don't know what happened to that one. We can cancel those two out, leaving f of x equals x plus 3. So it is a straight line, it's the graph of a straight line. However, it is still undefined at x equals -1, right? Because it made the original denominator equal to 0. Right? So rational functions, just a little note in the bottom there, rational functions can have point discontinuities as well as vertical asymptotes. If the rational expression can be simplified, the function is still not defined at this value of x, but the discontinuity becomes a point rather than a vertical line. So we don't have an asymptote anymore because we canceled, but it is still a hole in our graph. We still cannot use that point. Right? So we have a hole in our graph. All right, so we have a hole right there at -1, 2. But we want to find the limit of our function here, f of x, as x approaches -1. All right, so you can see if we come from the left-hand side and the right-hand side, the limit is still 2, even though there is a hole in the graph. Right? So it does not matter if your function is not defined at a point, so long as you're going to the same point as you approach from the left-hand side and the right-hand side. This one is in your notes. So this one is a piecewise function. Right? So we change the rule as we change which part of the domain we're in. Right? So this part here, that's just the graph of y equals 3 for anything that is less than or equal to 0. So notice that equals to 0 means that we have a filled in point there at 3. Right? So when x is 0, right, our function is 3. We use 2x squared if we are between 0 and 1. And we use 2x if x is greater than 1. So we just switch which rule we're using depending upon what the value of x is. All right, so we're going to evaluate the one-sided and two-sided limits here. Notes for you. All right, so we want to find the limit of f of x as x approaches 0 from the left. Right? So if we're, I don't want to use blue because the graph is in blue, let's use red. If we're coming from the left-hand side, right, the limit is approaching 3. Right? So as we come from the left, the function is approaching 3. If we come from the right, we're no longer approaching 3. Right? So we have what's called a jump discontinuity. There's a big break in our graph. Right? And so if we come from the right-hand side, the limit of f of x as x approaches 0 from the right-hand side, that's 0. Now how about the limit of our function as x approaches 0? Well, notice that the right-hand limit does not equal the left-hand limit. I'll just use a little abbreviation there. So that means that our limit is undefined there. It does not exist, right? Okay, well, actually, I don't want to say undefined. It just doesn't exist, right? There is no limit for as x approaches 0 because we're not headed to the same place from the right-hand side and the left-hand side. How about the limit of f of x as x approaches 1 from the left? Right? So as we're coming from the left, our function is approaching 2. The limit of f of x as x approaches 1 from the right, we're still approaching 2. So that means the limit of f of x as x approaches 1 is equal to 2, right? Because the right-hand limit equals the left-hand limit. So that limit does exist. Right? So we can find the limits at those values. Notice that our function is defined at f of 0. So even though the limit doesn't exist at 0, the function's defined at 0, right? F of 0 would be 3. And in the second case, the limit is, we do have a limit as x approaches 1, but the function is not defined at 1 because we have a hole in the graph there. Right? So you can have a limit, you can have a value, the function can be defined for a certain value of x, and the limit not exist. And then you can have the function not defined for a value of x, but the limit exists. Because the limit is not dependent on the function there being the function existing at that value of x. All it depends upon is that you're approaching the same point from the left-hand side and the right-hand side. And this one was in your notes as well. Okay. Moving on. Right, let's look at this one. Here we have the graph. I hope it's not too small for you to read, and some of the some things didn't print very well, so I kind of added them. They're not all limits of f of x as x approaches 1. Some of these were from the left and some of these were from the right. All right, so let's take a look at these. By the way, some of your homework problems for this this lesson will look very similar to the ones we're doing right here. All right, so as x approaches 1 from the left, right, the limit, so the value of the function is approaching 1. So our limit, our left-hand limit as x approaches 1 is 1. How about from the right-hand side? All right, so if we come towards 1 from the right, right, now that's not very straight. If we come from the right, there we go. Now our function is approaching 2. So the limit of f of x as x approaches 1 from the right is 2. So here, this limit does not exist because the left-hand limit does not equal the right-hand limit. Right? They're not the same. Right? So unless those two limits, as we come from the left and from the right, are the same, right, our limit is not going to exist. How about f of 1? Right? That does exist. When x is 1, the value of the function is 2. Right? So here the limit does not exist, but the value of the function does. All right, so let's take a look at the next one. All right, so we are looking at the limit as x approaches 1 from the left. We approach from the left. Right, our limit is going to be, let's just say that that's at -1. Can't be quite certain if it's a teensy bit up below, but I think it was intended to be at -1. Let's look at the limit as x approaches 1 from the right. Okay, so if we follow the function from the right, right, we see that our limit is equal to +1. Right, so the limit of f of x as x approaches 1, they're not the same from the left and the right. So this does not exist, right, and that's because our left-hand limit does not equal our right-hand limit. But the function is defined at 1, right, so that would be 0. Right, so your function can be defined at a point, but your limit not defined. And that's where this podcast is going to end. All right, see me in the next podcast, and we're going to take a look at the formal definition of limits. Bye for now.